Here I am with another chapter in my series on documenting all of the Heathkit digital multimeter models. And as usual, I'm going to start with Chuck Penson's excellent book, Heathkit Test Equipment Products. And I'm going to flip to the frequency counters and multimeters chapter. And as usual, I'm just going to give a quick recap of the history of the Heathkit digital multimeters. Heathkit's first digital multimeter was the IM-22, which was a 3.5 digit multimeter with Nixie tube display. Quite expensive. Pretty nice piece of gear actually for the time. I have one of these, but it has so many problems, in a lot of the parts that are bad are just not replaceable, so mine doesn't work. It lights up and things, but it doesn't work properly. Not long after that came out in 1972, actually released the same year, intended more for the hobbyist market, was the IM-2262, which was only 2.5 digits, but otherwise a reasonably useful meter just for casual use. Not enough precision or resolution for anything very serious, but still enough to be useful to a hobbyist. This was soon replaced after just 3 years when Heathkit decided to repackage it as a benchtop instead of a portable handheld or pseudo handheld device. Same circuit with just minor changes, and that's the IM-1212. This model here was produced by many different, or at least several different companies that had private labeled them, mostly technical trade schools. This was then replaced after just 1 year when Heathkit decided it's time to go from the Nixie tubes to LEDs, and the IM-1210 was that machine. It's again basically the same circuit as all three of these, but modified for an LED display. And the logic in here is almost entirely transistorized, as it was in these. There's no large monolithic analog to digital converter or anything like that. It's all done sort of brute force and with transistors. Anyway, the 1210 was made for about 6 years, up until 1982. Now meanwhile, Heathkit did have some meters that were intended for a little bit more professional or serious amateur or light industrial use, and those came out about midway through the IM-102. These are also 3.5 digits. The IM-2262 was a nice, solid, battery or AC operated digital multimeter using Panaplex displays. Beautiful display. And that was made for about 6 years. And just a couple years after that, Heathkit announced the IM-2212, which was again a 3.5 digit display, this time using LEDs, and this was Heathkit's first auto-ranging, and actually I think only auto-ranging digital multimeter. That was its claim to fame. It's actually a really nice meter. I have all of these meters here. I had to acquire them in order to do the documentary videos. And then same time around the time these meters came out, and midway through these meters, Heathkit introduced their first digital handheld multimeter, the IM-2215, which is actually a very nice piece of kit. And it's styled after, and its functions are equivalent to the Fluke 8020A, which was the world's first practical / successful handheld digital multimeter. And it's kind of like Heath got the idea to try to copy that without actually copying it, but to use the same general layout and the same functions and ranges and about the same size and shape of case to try to be competitive with that. Now, around the same time that these other guys were being discontinued, the early 80s, Heath replaced these and these, or this one, all 1982, 81. These models here all went away and were replaced by this series of 3 meters. The IM-2260, the IM-2262, and the IM-2264. Each one being a little better, with the 2260 being the base model, 2262 being the mid-range, 2264 being the deluxe. So specifications got a little better, features got a little better, more ranges and other features added. And in addition, the 2260 had an LED display, whereas the 2262 and the 2264 were LCD displays. And then also, around the same time that these were running out of steam, Heathkit introduced a replacement for the 2215 with another handheld digital multimeter, the IM-2320. Of these 3 meters, only the 2260, the base model in the series, was continued through until the time Heathkit exited the kit-making business. So it was essentially the most successful of the 3 models. So now that I've talked about all the different digital multimeters Heathkit made, the subject of this video is the IM-2262. I've already made a video on the 2260, it's up on YouTube, and now I'm going to do the same treatment for the 2262. Looking at what Chuck Penson's book said, of the 3 digital multimeters released in the summer of 1982 to replace the IM-1210 and IM-2212. The others in the series are the 2260 and 2264. They all have a 3.5 digit display. They're all designed to run on a set of 6 C cells, either alkalines or NiCad rechargeables. A power cube was sold as an option, and I do address that in this video. Now there's a mistake in the Penson book here. All of these say that they used a proprietary LSI or monolithic analog to digital converter chip, and that's not true. That was, I think, some information that was passed on to Chuck Penson that was based on erroneous information. They all use off-the-shelf Intersil 7107 or 7106 integrated monolithic analog to digital converter / display driver ICs, which are still made and available even today. So ignoring the part about these being custom and irreplaceable chips, we'll go on. Other than the display differences between the 2260 and the 2262, it's subtle enough that at first glance it's hard to figure out. Basic specifications are the same. The differences appear to be an expansion of the ranges available, and I didn't really see that except for the low end. It does add a low end, which the 2260 did not have. So one range, an order of magnitude lower than what would have been the lowest on the 2260. And addition of a true RMS measuring capability on AC circuits. The 2262 and 2264 were the only Heathkit true RMS reading digital multimeters. The 2262 was sold for only 1 year and was the first of the 3 units to be discontinued, gone by the catalog of the summer of 1983 and not replaced. I had a hard time finding these because they are fairly rare. And surprisingly, I had a hard time finding the 2264, but that'll be another video. So let's look at the front panel of this meter and see what we have. Starting on the right side, we have 2 primary jacks for test leads, the positive and the negative, or the positive and the common. This is the jack that's used for all inputs except for the 10 amp function and range. So all voltage ranges, all current ranges except for the 10 amp range, and all resistance ranges are accommodated by these two jacks. So you don't have to be moving your test leads around all the time. It's all handled by the switching inside the meter. Then there is the special 10 amp jack, which is only used for that upper range of the current function. We have, of course, the LCD display. There's the power switch with a little note saying to do diode testing, see the note on the rear of the meter, which has instructions. That's got nothing to do with the power switch. That's just where they had some free space to put the note. So there are DC volts and AC volts functions, and they are color coded over to 200 millivolt full scale, 2 volt full scale, 20 volts, 200 volts, and DC up to 1000 volts. And if you're on AC volts, it's the same, except the highest range is limited to 750. In reality, this is just a 2000 volt range, but the meter is not rated to go up to more than these numbers on the top range, even though electrically it's still a 2000 volt range. And then there's an additional voltage range, which is just for testing the voltage of the internal battery if there's one installed. And if you put it in this position or in this range, it's just a little note saying as long as you're greater than 6 volts, you're good. Below that, the meter may not be working quite properly. Then we have the amps ranges, DC amps and AC amps. Once again, color coded over. The lowest range is 200 microamps, then 2 milliamps, 20 milliamps, 200 milliamps, 2000 milliamps, or 2 amps. And then kind of hard to see is this number 10 here. That's white to be color coded with the white jack, but it kind of a misfire because normally that almost disappears and you don't realize there's actually a top range here for the amps. It just sort of disappears compared to the nice contrasty black. The white on the light blue is not all that visible. And then finally we have the ohms function, once again color coded. The lowest range is 200 ohms full scale, then 2 kilo ohms, 20K, 200K, 2000K, or 2 megs, and finally 20 mega ohms. The way Heathkit did this front panel is it's the same front panel they use for all the meters in this series, the IM-2260, which is an LED meter, the IM-2262, that's this one with an LCD display, and the IM-2264, which is very much like this, but it also has an analog meter here for peak detection, not for actually taking measurements, and there's an additional button here. So the aluminum front panel actually has cutouts for an additional button here, and there's also a hole up in this area somewhere, I think, I forget where it is, for a reset button for one of the functions. And of course there's a cutout here for the meter, should you have that. And it's, again, an aluminum faceplate with a laminated plastic graphic sheet over it. And then this piece here, which forms the bezel for the LCD display, is an additional layer that's just sort of glued on there with something equivalent to the adhesive used on double-sided sticky tape. And I forgot to mention in the part of this video when I talked about restoration, when I got this, it all looked okay, except it was kind of crinkly when I put any pressure here. And when I actually withdrew it from the case housing, all these layers delaminated. The plastic here came off the aluminum backing, and this piece here came off of this layer. So they were all separated. I ended up doing it with super glue. I used a gel formulation super glue around the peripheries and hit it with accelerant and then added the next layer and built it back up. I don't think it's as strong this way as it would have been originally, but at least it holds it together. I'm not really fond of this. I'm perfectly happy with LCD display meters, and of course these days pretty much everything except for laboratory bench type meters have LCDs, but I don't think it's as legible, as readable, as attractive as some of the other types of displays. And just looking around, I don't see where there's a lot of popularity even today for LCD displays on benchtop meters. Certainly there are models that have them, but things like the vacuum fluorescent displays on this B&K Precision, these are still very popular. They just somehow look more professional. Their viewing angle is really good. You can see them from far away and everything. Problem with displays like this is, you know, from the vintage these came in, this is pretty much what you were going to get. But the viewing angle's not that great on them. They're a lot harder to read from any distance away than the LED version of this meter. And kind of sitting back in here without any backlight even, it just has a reflector for ambient light to go through and bounce back out. So it's a retroreflective type LCD display. It's just not as good a viewing experience. The LED was better, I think, in just about every way for this series of meters. And it's too bad that the most capable models in the series, the 2262 and the 2264, were saddled with the kind of LCD display implementation that they had. Okay, here's the IM-2262 opened up. Let's start with the actual display board, which is the analog to digital subassembly. The board here contains the ICL7106. That's the monolithic intersil A to D converter chip and display driver that handles all of the functions associated with the LCD display. And it has a few support components. The capacitors in white and the brown capacitor there are all either associated with the clock or with the integration or the auto zero hold function, and the electrolytics there for the power supply. I think probably one of these caps is across the input to the either probably the input voltage to the chip. That's the most likely location for it. There's also a couple of diodes in there and a few resistors also associated with the dual slope integrator function or the clock oscillator. The 7106 directly drives the LCD, so there's not a lot of other components on the board. It mounts upside down and facing forward like this. It's connected by two ribbon cables that bring out power, things like decimal points, which are controlled down on this board. The 7106 does not control the decimal points, since it does not know which kind of input scaling is being used before it receives its signal, and thus it can't determine where the decimal point should be positioned. So that's handled down by some of the logic in this area. The 7106 also cannot handle things like the low battery indicator, and while it does normally control the minus sign at the left of the display, on this particular meter it does not directly control that, because there's additional logic on the main board that determines if you have a plus sign or a minus sign. That's sort of a deluxe feature here, that if the number is positive, it's not indicated by absence of a minus sign. It's indicated by actually displaying a positive sign or a plus sign. So the minus sign coming off the 7106 is routed down to logic on the main board, where it's conditioned, and then it determines if it should be the minus sign or a plus sign, and it generates the extra display signals for that. So the main board contains all of the input switching. There are the range switches and there are the function switches. They are soldered on both the tops and the bottoms of the switches. So the circuit board has the pins coming off the bottom of the switches, and then there's a lot of direct wiring point to point along the tops of the switches, mostly in regards to common busing, and in the case of things like the range switches and so on, there's a lot of signals that pass from one switch through another, and you can see the diagonal wires doing that. And let's see, the power switch is over here. This only switches the battery voltage. It does not switch AC power. No AC power enters this meter directly. There are a couple of terminal boards on there, and they hold this big capacitor, which is there if you are in the AC input mode, and it allows DC blocking. The IM-2260 meter, which is the lowest end model in this family of meters, does not use DC blocking, so it doesn't even have this capacitor. That's a function they added for this intermediate model. The 2264 is very similar to this, but it's at the top of the line, and it has everything this has plus some additional features. So let's get back to the board here. This device here in the circular can, which is not a transistor, as you can see from all the leads, that is an op amp, and you can see what kind of things were coming out. That some of the op amps on this board are in the circular packages, which were much more common at the time this meter came out, even though the circuit board was designed for the dip or dual inline package versions. It's still possible to plug the round ones in if you just bend their leads around so they line up with the dip sockets. Anyway, this op amp here is going to be for the input buffer that goes in between the scaling circuitry and the precision AC converter. As we get into the circuit discussion later on in this video, I'll talk about how this op amp and its surrounding components handle a critical function relating to range selection. It's done mostly through switches and a big precision laser trimmed voltage divider, which is this hybrid package here. But some of it's also done electronically, and that's what's going on in this area. Now, going around this side, the positive input jack is wired directly way over here to the beginning of the range switches, or the function switches, and then onto the range switches. The minus jack is directly connected down here to this part of the circuit board, and then the 10 amp jack also is connected directly down here. Now this first thing, which looks kind of odd, this tubular device with two leads on each end, that is a shunt resistor for the highest current value. I believe it's 0.01 ohms. And basically what they're doing here with the 4 leads is 2 of the leads go to the actual resistor that's in here, and the other 2 leads go to it, but they're only used for measuring. So the 10 amps, or up to 10 amps, flow through the resistor using 1 pair of leads, and then the voltage dropped across the resistor is measured using the other 2 leads. And then we have some additional shunt resistors here and here, and then some clamping diodes to protect the circuitry if you hook something really crazy up here. Let's see, going over here we've got some of our precision resistors that are used for calibration functions only. They are not part of the normal operation of the meter. They're just precision resistors that can be used to calibrate the ohms range trim pots, which are all over here. This op amp here is part of the precision constant current source circuit that includes these trim pots and several resistors in this area, and that's for the ohms mode. Some of these capacitors over here, some adjustable, some not, are used for some of the ranges in the voltage measuring part of the circuit. So along with the precision voltage divider, across some of those resistors that are in here are various combinations of fixed and adjustable capacitors, and those are trimmed during calibration of the meter. They're just AC compensation. This op amp here is, I believe, a quad NAND gate CMOS logic circuit, and that's part of the auto calibration function. Again, not part of the actual meter circuit. That's there to generate a precision AC signal that's used for calibrating the AC functions of this meter. And there's another chip of the same kind back here, and without checking the schematic offhand, I don't know exactly what that one is doing, but I believe it's part of the logic that determines which auto range function this meter should be in. You can see over here there's this big ribbon cable coming in. Comes over here, and it bends and comes over here and goes to a bunch of the range switches. And what that's doing is, in addition to the range switches directly switching signals around, some gangs of the switches are picked up by that ribbon cable and brought over here, where there are pull-up and pull-down resistors, and then over on the other side a bunch of diodes. There's some diode logic, and that's combined with some logic in this IC to determine if the meter should be engaging certain electronically switched range functions. For example, there's a times 10 range function, and part of that's going to determine when that should be engaged or not. This other logic down here, also more CMOS logic, that's associated with all of this too. It's trying to figure out things like, I already mentioned, determining whether the display should have a plus sign or a minus sign based on whether the minus sign is being driven by the 7106. And then there are some other functions in there as well, but it's all part of that same idea being implemented in CMOS logic. Now this other round can, this is not an op amp. This is a precision true RMS converter. And apparently that was only available in a round can because it does not have a dip pattern on the circuit board. That takes in the pre-scaled AC signals and produces a DC output that is proportional to the true RMS value of the waveform, whether it's sinusoidal, square wave, triangle, or other. That is something that in all of Heathkit's meters, only this 2262 and the slightly nicer 2264, these are the only Heathkit digital multimeters that had a true RMS function. And this was a pretty new thing, that it could be done in an IC like this when these meters were designed. So the other meter designs they had were older, and they just had normal simple averaging AC converters that would only give you a true reading if you had a sinusoidal waveform input signal. Let's see what else we have here. There's some more trim pots and things for various functions. And then this area over here in the corner is the power supply. That is there to generate the various power supply voltages required by the meter circuit. And there's going to be a plus and minus 8 volt and a plus and minus 12 volt. And those are all generated off of the single voltage coming off the batteries or off of an AC wall adapter. So a 9 volt input from the batteries or the AC wall adapter gets converted into those other voltages by this little circuit here. So having covered that, let's just take a look at the battery clip here. It has a label on it. There are some resistor values which are measured at the factory, and then the user is given a piece of paper with those written on it and instructed to transfer the numbers to this label, and those are for the voltages that are actually going to be measured at the low cal and high cal terminals, which are down here somewhere. Yeah, down here, low cal and high cal. That's for calibrating the voltage ranges of the meter. And then 4 different resistance measurements are available for setting up the trim pots down here and measuring these 4 resistors. These values here are of those 4 resistors. Here's an interesting tidbit. See how these precision resistors, they're the reference resistors for the ohms mode, they're set up off the board. Sometimes that's done if a resistor is likely to get kind of hot, and it's to give it more air space around it. In this instance, that's not what it's for. It's common with these very precise resistors that just the act of heating them up with the soldering can cause their values to shift slightly. And so when they're soldered to the board, it's common to mount them up so that when they are soldered, there's more distance of the wire lead between the device and where the soldering is happening, so that the actual resistor doesn't get the brunt of the soldering iron temperature. So that's why those are elevated. Here's this little circuit board that is for the power supply circuit. It has the AC wall adapter jack on it, and it takes care of switching the batteries in and out of the circuit depending on whether the AC adapter is plugged in or not. Alright, flipping this guy up on end. It's just the bottom of a double-sided circuit board, but there is this shield which covers the more sensitive front end circuitry. Just provides a little extra protection for those circuits. Here's the plastic case for the meter. It has a detent locking handle, which also can be used as a kickstand to hold it up at different angles. It's all plastic except for the spring and washer mechanism for the handles, and these 2 brackets that snap into the case and are used to hold the back panel and also hold the metal brackets at the rear of the circuit board to hold this whole assembly inside the case. To put the circuit board assembly into the case, you start by sticking the battery holder in from the front and pull it out the rear partially, and then stick the assembly in from the front, making sure not to catch the shield on the bottom on the rear of the case. And you get to a point where it's nearly all the way in, and the front panel recesses till it's in like that. At that point, these 2 brackets on the rear should line up with the holes in these brackets, and then 2 screws go in there to hold the whole thing together. So those screws are in like that. Then the only thing that's left is to put the battery pack and rear panel assembly on. And that goes in like this. The cord just folds up in there. Have to make sure not to pinch these wires. Some of them like to hang up on the brackets. And then 4 screws at the corners. So 4 screws in at the corners. Looking around the side, you can see how the handle acts as a bail or kickstand. And it basically just pulls out on the sides to disengage, and then it can lock in position for a carrying handle. It can even fold around the rear if you just want it out of the way when it's being used on a bench. And there's still enough room to get the wall adapter cord out and not have it hit the handle. So it's all back together. A little bit about the restoration on this unit. This was an eBay purchase, advertised as working, but as often the case, some things were wrong with it. This was bought along with another one, the 2264, from a fellow in Tennessee or Kentucky, I forget which, who said he had built both and used both of them in his lab until he had the downsize just due to age and so on. He wasn't using them anymore. And it looked like he did a pretty decent job of assembly. However, on this model, I found it was pretty dirty. It had a lot of crud that required disassembly of a lot of it to just get it cleaned up, get fingerprints and smudges and things off of the case. And I gave it a quick test of functionality, and it was basically all working, except there were little annoyances. One example of that would be that the low battery indicator was always on. And when I had it pulled apart, I realized that the NiCad batteries that were in it had badly leaked. There was a yellow fluid that was just all over the backside. Luckily, it mostly stayed within the battery holder area, but I had to dismantle that whole rear panel and do a lot of cleanup. And I started realizing that the reason the low battery indicator was on was because there were little splashes of that yellow fluid in various places on the circuit board, near the rear of the circuit board. And apparently it was conductive, and it was causing, for example, the circuit that detects low battery voltage is right there on the rear, practically touching the battery pack. So I had to use some of this flux remover with a spray, and I just saturated the rear of the circuit board and took the chips out of their sockets and blasted under there, tried to remove all of that fluid out from under sockets and out from under components and everything using this, and then blew it dry with an air duster, and then things like that low battery indicator just cleared up. And I didn't really have to do any other repairs. I started to do the calibration procedure on it, but mostly it was pretty good. And I'm going to go back and do a further calibration after I do this video. How am I going to power this meter? I'm not going to have batteries in it. I just hate having batteries locked up inside test equipment, bench test equipment, where they're normally not needed, and they're easily forgotten, and they're going to leak or something and cause all sorts of damage out of sight and out of mind. So for things like this, I'm always going to run it off the AC adapter and have no batteries installed. Heathkit had a product called the PS-2350, which was a wall wart type power supply, unregulated, somewhere in the ballpark of 8 to 9 volts under normal load for these meters. And I make these clones that are just based out of a inexpensive switching power supply wall wart that produces 9 volts regulated at about half of an amp. And I have these for all of the Heathkit meters that would use that original type of power pack. And I just cut off the normal barrel connector that these come with and put on a Switchcraft. I think it's the 850X, I think is the model number. Anyway, it's a 0.1 inch diameter micro or mini phone plug. And that's what Heath used on all of these for power supplies. And with the high quality structure on here, it's a black anodized machined aluminum housing. It's a perfect fit for these. What to do for test leads on these? As I acquire these meters, they almost never come with test leads. And if you go out and buy test leads for test equipment these days, they're almost always either the single shroud, like this Fluke 77, where you've got an exposed banana plug in there, but it's got a single shroud around it. That's for safety. And I think even this guy here has the same thing. But there's even dual shrouded connectors now, which entirely remove the possibility of making connections. Here's an example of that. So even the banana plug has a plastic tip on it. There is exposed metal behind there, but there's nothing you can get your fingers onto. You have to have a metal barrel that slides down between the inner and outer parts of those insulating components and then finally makes contact with the metal. So these are double shrouded. They have other names. Those leads will not work with meters of this vintage. And even companies like Pomona, who make great test leads and have a lot of different kinds, they no longer have anything that's really quite applicable for these unless you want to buy the components and make your own. I found these ICO ones. They're kind of cheap. They're, I don't know, $5 for a pair on Amazon. And they're intended exactly for use with vintage meters and other test equipment when you need to have plain unshrouded banana connected test leads. Now the other end of these particular leads is nothing special. They're just regular run-of-the-mill, no frills, hard point test leads, but they work for most things. Okay, on to the demonstration. So I'm going to turn this guy on, and we've got 0 volts and a plus sign displayed. I'm going to comment on that elsewhere in this video, but Heath decided to display positive numbers with a plus sign rather than just assume it's positive if no negative sign is displayed. So that's something you don't see on a lot of meters, but the 2262 and the 2264 had this feature. So I just got the meter connected up to my bench power supply. I'm going to go over and crank it down to 0 volts. I'm going to put this in 0 volt mode, and I'm going to start with the 20 volt range and turn the power supply on. And I'm sitting here with just 0.01 volts displayed. As soon as I bump the power supply up to 1 volt, I get the positive sign and 1.00 right smack on the money. Now the reason it was reading a negative number before is there is a zero control internal And since I've not touched up the calibration on this, it's biasing or offsetting the input voltage into the A to D converter very slightly negative. That's why when it should have been reading 0, it was reading minus 0.01. I'm not sure if I could really improve on that much with the calibration. I'll find out later, but for the purposes of this video, it's not really a problem. So 1 volt displayed for 1 volt applied. Let's go up to 6 volts. Pretty good. There's a little bit of inaccuracy there, probably. Again, that will improve with calibration. Let's go up to 12 volts. It's looking pretty good. Let's go to 23 volts, and it's overranged. I go to the 200 volt range, and it's reading 23, right on the money. And I can go up to 32 volts, which is as high as my bench power supply goes, and I'm pretty much right there. So good for that. I'm going to bump this down back to 24 volts. And the DC volts range is working just fine. I've put the meter into AC volts, and I've selected the 200 volt range because I'm going to test this function using my Variac. I have my AC power access box, which I have a YouTube video on, and that's connected to my Variac out here. I'll turn that guy on, I'll turn this on, and again, it's not calibrated, but it should be very close. I'm going to go up here to roughly 50 volts on the Variac, and I'm reading 48. And that's because I know historically this guy is reading just a little high on its meter. So yeah, pretty much 50 volts, that's working fine. Go up to around 100 volts. And it's just sitting here just south of 100 volts. Go up somewhere in the 140, 150 volt range. Yeah, and it's sitting just below 140. So AC volts is working. Okay, I've got the meter in DC amps mode, and I've selected the 20 milliamp full scale. I have my bench power supply set to 24 volts, and it's wired in series with this 4 to 20 milliamp current loop calibrator, so I have a way of controlling milliamp signals. And again, that's wired in series with the meter, and I don't have to move the test leads around because this meter only uses those two for normal measurements. So I'm going to turn on the power supply. I get the red LED here indicating that the loop is good and powered. And I look up on the display and I'm seeing plus 12.07 milliamps. Now if I throw this left-hand switch here, that'll force the transmitter to output 4 milliamps. And there we go, right on the money. Turn that back off, we go up to 12 milliamps. I throw the other switch, that should cause it to go to 20 milliamps, but I suspect will be overranged. So I have to go to the 200 milliamp range, and it's 20.1 milliamps, that's why it's overranged. That's the fault of this, it's not quite calibrated full scale. Go back to here, take the switch off, and I've got my 12 milliamps. I can turn this knob and change the milliamp value around. It's working just fine. Okay, milliamps is working. Turn off the loop power. As for testing AC current, I'm not actually going to demonstrate that, but the way these meters work is you have the front end scaling and switching for function, and then the additional scaling is selected here. The only difference between AC volts and DC volts is whether the signal gets routed through the AC converter after the range scaling. The AC converter converts AC input signals to DC so that the rest of the meter circuit, which knows only DC, can measure them. And we've already verified AC and DC volts. We've verified DC milliamps, and the only difference between that and AC milliamps is whether or not the signal goes through the AC converter, which we've already proven when measuring AC and DC volts. So, other than rigging up some lash up here in my lab to be able to measure AC volts, I'm just going to take it on faith that it's going to work perfectly fine because I've already tested all the circuit modules in here and I know it's going to work. So I'm going to briefly demonstrate the plus sign and the minus sign. I've got my power supply turned on. I'm going to stick my test leads into it with the correct polarity, and I see I've got about 24 volts and the positive sign is on. Now if I flip the test leads around and connect into there, now I've got the minus sign. Okay, we're going to test ohms now. So I've got it in the ohms function, and I'm going to start in the 2 kilo ohm. Well, let's go down to 200 ohm range. And I'm reading a little bit of quiescent resistance here. That's just the test leads and wiring inside this Heathkit decade resistance box. Let's crank her up to about 4 ohms. And we have about the same quiescent plus the 4 ohms. Go up to 8. Same quiescent and 8 ohms. So let's take that back down and go up into the tens range. Let's go up to 30 ohms. And we're really close. 70 ohms. Again, very close. The meter's probably more accurate than the resistors in here. Let's go up to 400 ohms, and of course we've overranged on the 200 ohm range here, so I'll go up to the 2K range. And it takes a moment to stabilize, but it's showing 400 ohms. But it's in kilo ohms, so it's 0.4 kilo ohms, which is 400 ohms. And let's go up to 600, and that's really right on the money. Let's add a couple of K to this. Let's go to 4K, and it overranges, so I have to go to the 20K range. And it's sitting in here at 4.59 kilo ohms. I have 4 kilo ohms here and 6 here, so should be 4.6 kilo ohms, and we're basically right there. Let's bring in the 10K range and go to 60. Once again, I've overranged, so I have to go to the 200K. And I should be reading 64.6K. So, yeah, it's a little bit off. And I think that would be improved if I actually went through the calibration procedure and tweaked this range a little bit. It was better in the lower ranges. Now I got into the 200K range and I'm seeing a little bit of inaccuracy, but it's still pretty close. So let's go and bring the 100K in here. I'm going to go to 800K, and I've overranged, so I go to the 2000K. And it should be 864. Yeah, not too far off. A couple of points on the lowest digit, but basically right where it should be. So I'm cranking all these back down. Back to 0. So this has a diode tester which both tests the basic functionality of the diode, but also lets you know the forward voltage drop or the forward voltage of the diode. I have here a typical silicon diode. I think it's a 4004. And you have to put it in the 2K range and select both DC volts and ohms. And normally pushing one of these will deselect another one. But it does allow pushing the DC volts and ohms at the same time. If I connect up the diode, and I have some little grabber clips extending out the test leads, and I'm connecting with the positive to the anode and the black to the cathode, so the diode is forward biased, and the meter is reading 0.58 something, and that's volts in this case, even though we're in the ohms mode. In this instance, it actually uses the constant current source of the ohms mode circuit to put a constant 1 milliamp through the diode, and then it measures the DC voltage across it. That's why it's in both modes at the same time. And that's about what we should get, because a typical silicon diode with 1 milliamp through it, at least this type of diode, the forward voltage varies a little bit on diodes like this depending on the current, but basically 0.6 volts is the rule of thumb, and this is really close to that, so it's certainly accurate. Now to check the diode in reverse, I have to get rid of the ohms mode, so I have to push something else and then put it back into ohms, and I should select the 20 meg range so I can read nearer infinity. And now with the diode connected reverse, I'm just reading infinity here, so that's indicating that there is essentially no leakage in the reverse direction. So it's a good diode, and we know it's a silicon diode because the forward voltage is about 0.6 volts, and that everything looks good with that diode. That's the degree of diode testing that can be done with this meter, and that's how it's done. So one more thing, let's do the battery test. I've got it in DC volts, and I'm going to select the battery test range, and the meter's reading what it thinks is the battery voltage, which is the output of my AC power adapter. It's approximately 9 volts, so that's working. Okay, here's the beauty shot. Yeah, that LCD is, it's not horrible in terms of viewing angle. You can read it, you know, whatever that is, about 30 degrees off axis and still have it be reasonable. And you can read it, you know, about the same number of degrees above and below, so it's not a horrible LCD in that regard. Alright, let's do a quick look at the Heathkit manual for the IM-2262. This version of the manual is dated 1982. So it's a nice thick manual. You're getting into equipment that's a little more complicated. So a lot more building and a lot of instructions and so on. So you've got your table of contents, introduction, and then you get right into the unpacking instructions, some assembly notes. Heath was always very good about making sure even relatively unskilled people could navigate and do what they needed to do. Component identification, how to handle circuit boards, parts list for the main circuit board, and then we get into the step-by-step instructions, which is very much step-by-step, and as it teaches you things, it doesn't need to repeat them over and over again, but You get into lead bending and how to solder and proper technique. And we just go through and, as usual, it identifies the parts of the board that we're going to be working on. Working on just parts of it at a time. The usual high quality illustrations. Making sure everything's very clear. They definitely did not skimp on the illustrations. Tons of illustrations for each manual. The all-critical step of getting the switches assembled correctly. How to deal with resistors that are mounted on their ends. I'm skipping some pages here. Now we're getting into connecting some of the wire looms to the circuit boards. Now we get to the analog to digital converter and display circuit boards. A lot fewer parts. And then the zebra strips for the LCD and assembly of that whole subassembly. Then we get into the basic chassis. And this is talking about what I already illustrated, that you've got an aluminum faceplate, that's the structural faceplate, and because it's used for all three models in this series, it has the cutout that'll accommodate either the LCD or the LED display, plus it has a cutout for the peak indicating analog meter, all three jacks, all push buttons, even the one that's not used on this model. There's a cutout for that switch. The 2264 does have a switch in that position. And then there's an adhesive back, laminated plastic panel that has, it's basically a glorified label, but it's in multiple laminated layers that have all the different colors on them. And then that gets stuck onto here. And then there's this bezel that's just molded brownish plastic. And then also the little Heathkit model number label. So 4 different things get put together into that subassembly. Mounting the circuit boards, the shield on the back, power switch, and oh no, that's the small circuit board for the AC power adapter socket. Putting the feet on the bottom, mounting the battery holder, mounting the handle hardware, and you even get to build your own test leads, which never seem to follow these meters when you obtain them on eBay. Basic checks to make sure you haven't done something really stupid, and a bunch of tables in case you have and how to correct it. Operational tests and steps you go through if those don't all work out the way they're supposed to. Lots of pages of things, and then finally calibration. There's a couple of reference capacitors which are used, and they've just been taped inside a small bag here. So the number of adjustments isn't really that high. You can do the coarse adjustments pretty quickly by just turning most of the trim pots full counterclockwise or to their center of rotation. And then the fine adjustments start out with, you can make a choice on whether you want to use the built-in references that are already in the meter, and that's something Heathkit did that a lot of other manufacturers didn't do or didn't do as well. You can actually get it to meet its published specifications without any other test equipment. You don't need another meter to calibrate this meter. But you can get it even better than the built-in references if you have higher quality references. I dare say most people just use the built-in references method. So you do a few steps to get the DC volts calibrated, then a few more steps to get the AC volts. Ohms is pretty simple. only one page dedicated to that. Then you go to the laboratory standards for DC volts, AC volts, and ohms. And there are no other calibration steps. Final assembly of the cabinet, and then many pages, a big thick section still of all the things you might want to know about using the meter in all sorts of ways. There's a lot of stuff on here about understanding the fine points of what it means to have a true RMS meter. Talks about diode and transistor testing, then a big in case of difficulty section, lots of troubleshooting, precautions and procedures, troubleshooting charts, quite a few of those. Then specifications, one page for DC volts, one page for AC volts, one page for DC amps, one page for AC amps, one page for ohms, and one page of general specifications. Then we get into the circuit description, still a fairly substantial piece of writing and illustration here. They go through all the fine points of how the A to D converter works, how the reference voltage is generated. I haven't read any of this. I may still study it just for fun. Talks about how the LCD is operated by in-phase and out-of-phase square wave signals applied to the segment and the backplane. Talks about the wideband buffer circuit, function range and control switching, the various converter circuits such as the true RMS converter, the ohm meter constant current source, the various parts of the power supply, the battery charging circuit, and then the calibration references that are built in, such as the DC calibration test points, the AC calibration, which comes out of an internal function generator, resistance calibration, which uses the internal precision resistors that are there for that purpose, and then finally semiconductor identification charts. When possible, it gives you the generic part number and the Heathkit part number and the component identifier within the kit. And it gives you the pinouts of the LCD, all the integrated circuits. And there we are. We're at the back where you can call customer service. But wait, there's more. There's this huge illustration booklet, the kind of thing Heath started doing more and more of as time went on. So you could have it folded out separately from whatever page of the manual you're looking at. So there's a lot more pictorials of circuit board components, mechanical components, wiring to the main circuit board, preparing the wiring harnesses, additional wiring harnesses to the main circuit board, and preparing that harness. All of the jumpers that are made on the tops of the switches, and they're encouraging you to use a wire wrapping technique for that. And then some soldered connections to the tops of the switches, two different parts of that, A to D and display circuit boards parts, wiring harnesses, all the mechanical parts for the case and the front and rear panels, some more assembly diagrams, the wiring harnesses to the power jacks between the different circuit boards, to the rear power jack, how that's wired up, assembly of the case halves and the handle, and then we're getting into diagrams here that talk about various test points and things on the main circuit board. Some mention of solder blob jumpers or solder bridge jumpers, which are used for various troubleshooting steps, and they're either on the front or the rear of the circuit board. I think mostly on the rear. Talks about setting up the various trim pots and trim capacitors, mounting the A to D and display circuit board to the main assembly, assembling everything into the case, and then pictorials of the front and rear panels, test waveforms for troubleshooting, more test waveforms, a block diagram of the entire circuit, and then your circuit X-ray views, or the circuit board X-ray views. The display board in gray and red, that's a double-sided board. The analog to digital converter board is single-sided. And here's something that really ticked me off. I don't know if I had a misprinted manual or if they all came out this way. This is a double-sided board, the main circuit board, and it's only showing one side of it. It's not much of an X-ray view if it doesn't show both sides of the circuit board. And nothing on the back. And of course the very large fold-out schematic diagram, which I'll get into in more detail later on. Okay, let's look at the schematic for the 2262. Now this is sort of a Franken schematic here. I've pieced it and taped it together from photocopies I've made on my small office copier. The original is huge, and I've both reduced it a little bit and tried to leave out extraneous parts that take up additional space. And I've made this copy mostly so I have something more manageable on my desktop and something I can mark up without defacing the original. And I did my circuit analysis and study using this copy here. I pasted this in, it's overlaying some of the notes, but it is again the IM-2262 digital multimeter schematic dating from 1982. So this is half the schematic, and then we flip her over and there's a whole lot more. Because this is so unmanageable, I'm going to do almost all of the subsections using my usual method of my redrawn sketches of each circuit section. But I will talk about here the basic features of the 7106 because I don't have a separate sketch for that. So the 7106 is actually the ICL 7106 chip made by Intersil. It's based on the 429100 if I remember correctly, which was a Fluke chip that did basically the same thing, and that was developed in collaboration with Fluke for a collaboration with Fluke and Intersil, and intended for Fluke's 8020A digital handheld multimeter, the first successful one of its kind in the world. And the 7106 is nearly the same chip. It's just modified slightly so that it's not exactly copying the proprietary Fluke part. Anyway, so this does everything. It's a differential input, so it has two different inputs, each of them differential. There's one that's the reference voltage, there's a high and a low pin, and it takes a differential reading of whatever voltage is out there. Just think of it like two test leads of a small meter that's inside the chip. And then there's another one just like it that measures the so-called input voltage, also differentially. And then the chip internally takes the ratio of the two signals, the reference input and the regular input, takes the ratio of them, multiplies that ratio by 1000, and that's the number that it will display. You can set up the 4106 to use different ranges of voltages or different spans, but normally you're going to have either 0.1 on the reference and 0.2 on the input as a full scale value, or you're going to have 1 volt on the reference and 2 volts as a full scale input on the input here. In this instance, the chip is set up to look for 1 volt here and 2 volts here. The chip requires an oscillator. It has its internal oscillator, although it can use an external one, and it can use an RC oscillator based on these two components, or it can use a crystal. It has a reference capacitor that's external. It has the components associated with the actual analog to digital converter functionality, including a buffer circuit with a couple of resistors, an integrating capacitor for the dual slope integration, which is how it determines what the input value is, and it also has an auto zero function where it can cancel out any internal biases that skew the value. And as part of its dual slope integration, there's actually several parts to each measurement cycle, and one of those is sort of sussing out what the internal bias is, storing that value in this capacitor, then doing the analog to digital conversion, and then subtracting the bias from that so that you don't have the bias in the actual output or displayed signal. So that's what these components here are doing. They're all part of that functionality. Then the vast majority of the pins on the chip are just the drive signals going out to the display. Now I'll talk about the power supply. The 7106 nominally works off of a single pole power supply. It does not require a plus and minus power supply. So it's expecting something in the range of 6 to 9 volts. 9 volts is because, again, this is based on the 4290-100 IC by Fluke. That was designed to run off of a 9 volt battery. So this is happy as a clam if you give it somewhere in the ballpark of a 9 volt supply, and that's applied to VDD here. Then VSS is the opposite side, and that can be any number of things, but in this instance it's tied to the minus 8 volt supply. It could just be tied to circuit ground, but in this instance it's a little bit negative, and that's because you have a voltage divider here, 6800 ohms over 1000 ohms, so almost a 7-to-1 ratio with negative 8 volts applied here, and that results in about a minus 6 volt potential that's applied to the VSS. That doesn't have to be done that way. This could be just tied to ground, but Heathkit decided to move it a little bit negative for this particular circuit. There are some internal voltage references that are developed. There is essentially a Zener diode between the VDD power supply input and the test output that produces a voltage of approximately 3 volts when you have an 8 volt supply here. It's essentially 5 volts less than whatever this is, so 8 volts minus 5 gives me the 3 volts that are coming out of this test pin. If this was a 9 volt signal up here, 9 volt power supply, then this would be closer to 4 volts. It's not really important exactly what it is. Now, in addition to the test being an output of a reference voltage, it's also an input. So if you short this point to ground, or not to ground, but if you tie it to the same voltage as the positive power supply, it forces the chip to turn on all segments of the display, so it acts as a lamp test or display driver test, or display test. So a double function on the test pin, that's why it's called test. There's a common pin which is established at 3 volts less than the positive voltage here, so 5 volts. And that can be used in various ways in the circuit. It's not strictly necessary, it's not an input, and it doesn't really have to drive anything. It's there to establish a common mode reference for the input voltages so they don't drift too far away from what the internal circuits can handle. Because as I said before, these are differential inputs, the reference and the input, and they're almost floating, but if they go too far towards the positive power supply or the negative power supply, then the chip can't work properly. So tying them in some way to this common pin keeps them within the common mode range of the IC, and everything will be hunky-dory. So in this particular meter, that's the only way the COM signal is being used. It's tied through a resistor to the positive 8 volt power supply, and thereby establishing that common mode reference. There's also a backplane signal. LCDs have a backplane, and I'll talk about that more when I'm discussing the way that the decimal points and so on are operated. But essentially, the outputs here going to the LCD segments are all square wave signals, and I don't know what the frequency is, but they alternate between the positive power supply and the test voltage, in other words 3 volts, so they're alternating between 8 volts and 3 volts, square wave going up and down between those. And if you want a particular segment to become visible, the square wave that's applied to the segment has to be 180 degrees out of phase with the signal that's applied to the backplane that's behind all segments. And if you make both of them the same phase or in phase with each other, then that particular segment will be invisible. So the internal logic of the IC takes care of all of that, in addition to knowing which ones it's supposed to be making visible at any given time to display the correct number. The backplane signal is output here and goes to the display. It's also used by some internal logic, primarily for operation of the plus and minus and the decimal points. And there's also a sign output. The 7106 knows when the input is a positive or a negative signal, and when it's negative, it's going to turn on the sign output, which is just another segment, but it turns on the minus sign part of the display to let you know that there's a negative value. Now in this particular meter circuit, it's not quite that simple. The sign output is intercepted by this logic here, which when it's appropriate lets it pass through to the minus sign on the display, but when it's also appropriate in certain functions, if the negative sign is not turned on here, then this logic detects it and generates the signals to turn all of these segments on to form a plus sign. Let's see, I don't think there's anything else I need to talk to about the 7106. We're going to go right on to the detailed circuit analysis now. Alright, let's start with the input range selections. This sketch covers the volts and amps primarily. This is pretty close to being a classic circuit for almost any multimeter. So we have the plus and minus terminals for the test leads. The minus or COM terminal is always connected to circuit ground. Let's start out with volts. Whether it's DC or AC volts, there's the two separate switches. They're almost paralleled, except in AC volts mode, the signal has to go through a blocking capacitor that blocks any DC component and only allows AC to go through. In DC, then DC signals go this way. We're presented with a precision resistor voltage divider comprised of 3 resistors, 9-point 9 mega ohms, 90K, and 100K. So in a normal divider that goes in decade ranges, you'd start out with the 10K and the 90K, and then you'd go to maybe 900K and so on. But in this instance, it's only got the 3 resistors with 2 taps. If you're in the 200 milliamp range or 200 millivolt range, then the signal is passed through this switch here. All these switches are shown in their normal positions. If they're actuated by being pushed in, then it goes to the upper position. So if we're in the 200 millivolt range, the input signal from the positive test lead just goes straight through this switch and then propagates down through all of the other range switches and then on out on its way to the input of the A to D converter. If we select the 2 volt range, the same thing happens. So there's no difference here in this part of the circuit whether in the 200 millivolt range or the 2 volt range. However, if we go to the 20 volt range, now we tap off the voltage divider here and the signal propagates through. We get the same exact switching if we were in the 200 volt range. Then finally, if we're in the 1000 volt range, then we tap off here. And that's the only range that uses this position in the divider. Then there's finally the battery test switch. The battery switch reads off of the battery voltage by way of a resistor voltage divider with a 113K resistor on top and a 1150 ohm resistor on the bottom to ground. As an example, if the battery is at 6 volts, there will be a 0.06 volt potential here, and that will have to be then conditioned on its way to the analog to digital converter. Now this is probably a good point to mention that the reason that this works here with every other range being at a different step in the resistor divider, this works because if we're in the 200 millivolt range, some circuitry down here will multiply that signal by 10. There's a times 10 amplifier later on in the circuit. So that will be engaged for the 200 millivolt range, which will boost it to a 2 volt signal. However, if we're in the 2 volt range, even though we tap off the same place when we're in 2 volts, the other circuit will be in a times 1 mode. So by that expedient, you still end up with a 0 to 2 volt signal, regardless of which of these you pick. The same thing happens with the 20 and 20 or 200 volt range. If we're in the 200 volt, the signal gets amplified by 10, and if it's in the 200, it gets amplified by 1. And I put that in a chart here. In the 200 millivolt range, we get 0.2 volts, and that needs to be amplified to 2 volts. However, if we're already in 2 volts, it just stays as 2 volts. In the 20 volt range, we get a 0.2 volt signal, which gets amplified to 2 volts. If we're in the 200 volt range, we end up with 2 volts anyway. If we go to the 1000 volt range, which even though it's limited to 1000, it's functionally 2000, and therefore it's essentially a 2 volt range like this is, but it's only going to go up to 1 volt. And if you're in AC volts, it's limited to 750, but it's still in the same overall range, so you end up with a 0.75 volt signal. So, as I wrote here, it's in the times 10 mode in the 200 millivolt range and the 20 volt range, and that's it. All other voltage ranges are in a ×1 mode or no amplification mode. I'll talk about the amplification later. Getting back to the battery test, a 6 volt on the battery gets attenuated here to 0.06 volts, but because it's in the battery test mode, it'll be a ×10, so that gets amplified from 0.06 volts to 0.6 volts. And the A to D converter thinks that that's in a 2 volt range, so if you think about that as being up to a count of 2,000, or actually 1,999, you're a order of magnitude down from that and trying to display 6. So it's going to end up displaying 600, and the decimal point control logic is going to put the decimal point here. So it'll read as 6.00 volts. Anyway, getting back to this, we have this signal which is either 0 to 0.2 volts or 0 to 2 volts depending on the range. And if we're in DC volts, it just goes straight through here, and it's presented to the buffer amplifier circuit, which I'll discuss later because it's on a separate sketch. And the signal exits that, but this is where the ×1 or ×10 occurs. The buffer amp has a gain of either 1x or 10x depending on the function and range. It's ×x for 200 millivolts or 20 volts, and also for the 2 mega ohm ranges if you're in ohms. If it's a DC signal, the signal exits here from the buffer amp. It has a little filter on it, and then if we're in DC volts, the signal propagates around this way and is finally filtered once more and then presented to the input of the analog to digital converter, which is expecting a 0 to 2 volt signal. Two volts. 2 volts max. If we're in AC volts, really the same routing occurs, except as I mentioned before, the signal goes through the DC blocking capacitor. It's presented to the rough range selection resistor divider, comes out of that, and gets routed through the AC volt switch here, which ends up going to the same place. It goes to the buffer amp, but now it has to exit over here after being turned from an AC signal to a DC signal. It exits here and runs through the AC volt switch and out this way and onto the A to D converter. Now what if we're in the amps mode? An external current has to enter the meter on the plus terminal, flow through something here, come back out via the meter ground, and then out and continue on its way. So the current comes this way, it goes through either the DC amps or the AC amps mode or function switch. It's got a 3 amp fuse, and then there's this diode clamping bit of circuitry there. So this node here is held at essentially 8 volts from the 8 volt power supply through this 10K resistor. So this is sitting out here at a high impedance 8 volt potential, and if enough voltage is dropped across the current shunts by the current coming through here, then this will eventually rise to a point where it's more than 8 volts, in which case the diode here becomes forward biased, and then current can flow this way to ground, and that would cause the fuse to blow. If it's a negative, then the same thing happens in the other direction with a minus 8 volt here and the same circuit but turned upside down. So either way, this point here is clamped to approximately 8 volts. So to continue with this, we've got our current coming in this way, and presuming it's not clamped and the fuse isn't blown, it's applied to this big current shunt series of resistors back to ground, and from there back here and on out of the meter. The resistors are 900 ohms, 90 ohms, 9 ohms, 0.9 ohms, and 1 ohm, which all adds up to 1K maximum, 1000 ohms. If you're in the 200 microamp range and you have 200 microamps running through here, that's 200 microamps running through this entire 1K resistor. So let's look at this. 200 microamps times 1K ohm equals 0.2. So that's the voltage you would get across this, and hence I wrote 0.2 volts full scale on each range. If you've only got 2 milliamps, then this switch is closed, and the 2 milliamps flows this way and through only 100 ohms, and you still get 0.2 volts, and so on, all the way down up to 2 amps or 2000 milliamps across, through a 0.1 ohm resistor still gets you 0.2 volts full scale. And that voltage is then monitored or tapped off through the remaining resistors or straight off the top. It doesn't matter at that point, because now we're not dealing with current, now we're just measuring voltage by a high impedance measuring circuit through a very low resistance here, so these extra resistors matter nothing. If the current is going this way, for example, and developing 0.2 volts maximum across this, then measuring that voltage through these other resistors, it's as if they're not even there. And we end up with our 0.2 volt potential coming out this way. We're applied to the 10 amp range switch, which is the switch after this one. And assuming that you're not in the 10 amp range switch, then that 0.2 volts continues on. It goes back around, and it's applied to the top of this set of switches. Then it ripples through, it's not in DC amps, it ripples through, it's not in AC volts, ripples through, it's not in DC volts, and it's applied to that buffer amp. All amps range use the times 10 mode of the buffer amp, period. So that 0.2 volts we got out of here, when it goes through the buffer amp, it's boosted up to 2 volts. And it continues on, and that's what the A to D is expecting to see for full scale. Now for the 10 amp range, we have a separate jack. It has its own shunt, just like these shunts were used if the current is coming in here. But if the current is coming in here, it just goes to this 0.01 ohm resistor back to common and then out this way. Well, at 10 amps you end up with 0.1 volts, and since that's going to get amplified by 10, it becomes 1 volt, and that's applied to the A to D converter. So let's see, the only other thing that's in here is a little bit of the ohms function, and it only shows part of it here. The entire picture is going to be shown on my separate sketch for the ohms range function, so I just showed a little bit of here just to be complete. So here's my sketch of the ohms ranges. We have all of the ohms range switches from 200 ohms to 2K ohms, 20K, 200K, 2000K or 2 meg, and 20 meg. And those are switched out through fixed precision resistors and some trim pots. and then they end up coming this way through this transistor, on out through these inconsequential resistors. And if you're not in ohms mode, it just goes to ground. But if you are in ohms mode, it continues this way, goes out the plus terminal, goes through the resistor under test, back in the COM terminal, and to circuit ground. So that's the basic route for measuring resistance or measuring in ohms. The idea being that this circuit's going to regulate the current going out to a fixed regulated current. And if we know the current going through the resistor, then we can calculate what the voltage drop is and how that correlates to the resistance. It will always be proportional as long as we know the current. And because this circuit regulates the current, then it's a simple matter to determine the resistance from the voltage drop. So how does that current regulation work? Well, let's start out with the reference circuit. Plus 8 volts up here is applied to this IC. It's a 2-terminal IC, and it functions like a more advanced kind of Zener diode, except it's temperature stabilized and everything. And it produces a precise 1.2 volts across it. Then there's a resistor and a switch to ground, which is closed when you're in ohms mode. So essentially we've got 8 volts here and 1.2 volts less than that, or 6.8 volts on the other side, and the rest of the voltage is dropped across this resistor. This precision voltage reference has got a filter capacitor on it, and it also has a resistor voltage divider. With 8 volts here and 6.8 volts there, you end up with still 1.2 volts across this, since that's what's across all of this. If you do Ohm's law on it, you end up with 0.41 volts here and 0.79 volts here. If we subtract the 0.41 volt voltage drop from the 8 volts, which is a regulated voltage, then we end up with 7.6 volts here. And that's applied to the plus input of this op-amp. Let's say nothing has happened out here yet, so this transistor is turned off. And let's say we're in the 200 ohm range, so this switch is closed. You have a path from plus 8 volts through this resistor, 374 ohms, this trim potentiometer, nominally 100 volts, or 100 ohms, and on down and out this way, but it can't get past this transistor that's turned off, so there's no current flow this way. If there's no current flow, then there's no voltage drop, and if there's no voltage drop, then the 8 volts here is applied directly through here to this point, and thus to the input, the minus input or inverting input of this op-amp. So what do we have here? We've got 8 volts on the inverting input and 7.6 volts on the non-inverting input. That means that the op-amp is going to try to put its output in the negative direction. It's going to go towards its negative power rail of minus 0.12 volts. That's applied to this FET, this, I believe that's a P-channel FET. A negative voltage here is going to cause that to conduct. So this is going to present a path this way. You get some current flowing through here, and now there's a voltage drop, and now there's voltage applied here, which turns this transistor on. And the next thing you know, you do have current flowing through this transistor and on out, as we talked about earlier. Now with a current path flowing out this way, now we do have a voltage drop across these two resistors, which means that we no longer have 8 volts here. If we no longer have 8 volts here, then the inverting input is lower than it was before, And let's just say that there's enough of a voltage drop to get this voltage to be less than 7.6 volts, in which case now the non-inverting input has more voltage on it than the inverting input, so the op-amp will start sending its output positive towards the plus 12 volt power supply. That turns this FET off, which turns this transistor off, which means the current stops. What's going to happen then is this op-amp will constantly be adjusting its output to result in enough conductivity here and here to result in a current flow here that results in a voltage drop here that ends up with 7.6 volts here. And with 7.6 volts here, you're in stasis, and the amp isn't going to adjust its output up or down. It's just going to stay at whatever voltage is necessary here to result in 7.6 volts here. And by that way we have regulation, we have negative feedback, and we have a precise current coming out of here that will not change regardless of what we do way over here, because this resistor is not in the feedback loop here, so this resistance does not affect the current, but we do have a regulated current going this way. If I instead change to a different range here, now we have a different resistance here, so there's a different voltage drop for a particular amount of current flow. Therefore you'll end up with a different voltage here, and therefore a different amount of current to still get 7.6 volts at the end of the day. And the same thing happens for these other ranges. Now I mentioned before that all of the voltages dropped across the resistor under test have to be monitored somehow. So we do tap off it right at the plus terminal through a switch which is closed in the ohms position, and that's applied to the input range circuit that I've already talked about. This switch here is the same as this switch here. So the monitored voltage across the resistance under test is applied this way, and since we're not in AC volts or DC or AC amps or DC amps or AC volts or DC volts, that measured voltage drop just goes all the way through here. It goes through the buffer amp, and since the buffer amp is programmed to be a times 10 amp when you're in most of the ohms ranges, that gets done and you end up with a signal going into the A to D converter of 2 volts full scale regardless of ohms range. Now I said that's with the exception of the 20 meg range. So a couple of things are different with the 20 meg range. First off, we don't have a pot to adjust the 20 meg range. Instead we just go through a different amount of resistance on the same circuit as the 2 meg range, everything else here being the same. So we change the amount of current that's going out, but we also switch gears on the buffer amp. It then becomes a times 1 amplification factor, and we end up with the same input to the AD converter that is a 2 volt full scale for 20 megs. So let's see, what else is in here? Well, this should always be positive because there's no voltage applied out here. We have a plus 8 volt here. Any voltages out here should be positive in normal operation. If they are, this diode is reverse biased, it does not conduct, and it's as if it's not even there. But if we hooked up some voltage out here that resulted in a positive or a negative voltage here, now this diode would be forward biased, and this diode would act like a short circuit from ground to this point, which is the same as putting a short circuit here, and thereby protecting all this circuitry in case of a negative voltage applied out here. So having already talked about what happens if we apply a negative voltage out here instead of a resistor, this diode will then become forward biased and it will shunt the input and prevent any voltage from being developed there. We need to be able to do something similar when it's positive biased, if a positive voltage is applied out here, but we have to do it in such a way that it does not interfere with the normal operation of the meter in ohms mode, because we are normally developing some voltage across this resistor as a result of the current going through it. So we have to make sure we don't do any shunting until we get well above that. So the way that's done here is we have in ohms mode, this switch here is closed, and we have 8 volts up here through a resistor through a 4.3 volt Zener diode to ground. So we're developing a 4.3 volt reference right here. If this voltage here should get to be higher than 4.3 volts plus the forward drop of this, so it's getting really close to 5 volts at that point. If this point rises above about 5 volts, then this diode will become forward biased and it will start conducting down through the Zener diode to ground, and that will result in this being sort of kind of clamped, although not as thoroughly as it would be in the negative direction. But again, it's there to protect the circuitry. During some conditions of weird stuff being connected out here, you could end up with a situation where you have a fair amount of current going this way, and there's this positive temperature coefficient resistor here, which increases its resistance as its temperature goes up. So some heating will result from a lot of current flowing through here, and that will cause the resistance to go up, further reducing the current and thereby reducing the heating. So it's a self-protecting circuit element here. And then there's also just a resistor here to drop some voltage in case of these shunting operations here. Because there is no actual fuse here to blow, I may have mentioned before that maybe we'd blow a fuse here. If I did, I was mistaken. We don't have a fuse to blow here, but what we do have is a resistor to drop voltage across if you're shunting with these diodes, and also this positive temperature coefficient resistor that will greatly increase the resistance to protect everything here and keep things from getting out of hand. So the only other thing to mention on the ohms mode is the reference resistors. There are 4 reference resistors: 1900 ohms, 19K, 190K, and 1.8 meg. And those are used in the calibration of the meter. So with that, you could calibrate the 2K range, that's this trim pot, the 20K range, that's this trim pot, the 200K range, it's this trim pot, and the 2000K or 2 meg range, that's this trim pot. So these trim pots here, except for the 200 ohm cal, are all calibratable using this resistor. I haven't read the manual's calibration instructions for how to adjust the 200 ohm cal. Probably there's a suitable resistor somewhere else in the circuit that could be used, or maybe the 200 ohm is just adjusted using the 1900 ohm resistor. Well, no, that would be overrange, wouldn't it? That wouldn't work. There's probably some suitable resistor below 200 ohms that can be tied into while calibrating this. But anyway, that covers, I think, all the ohms range functionality. Alright, let's look at the schematic for the buffer amplifier and AC converter. This is what follows the input scaling that we've already talked about. This schematic is divided into two halves. The first part is the buffer amplifier. The second part is the true RMS AC converter. Focusing on the buffer amplifier only, it has a couple of functions. One is it provides some sort of gain to the signal coming off of the input scaling on its way to the analog to digital converter. And it also provides some filtering when the signal is DC. So we come in from the input switching. There's a 120K resistor, which is negligible since it's going only into the positive input of an op-amp with nothing else in between. And this is a nearly infinite resistance here, so this is effectively like nothing. However, there is a voltage clamping function here, and this resistor does serve a purpose in regards to that. If somehow an input gets applied that results in too high of a voltage here, then one of these two FETs, which are wired as if they were Zener diodes, going to plus 8 volts or minus 8 volts, if those start to conduct to limit the voltage here, then the extra voltage is dropped across this resistor. And that's why it's 1 watt, because under some conditions it could be dissipating a bit of power for however long it takes the operator to realize what they've done. Now if there's an AC signal coming through here, then this value is adjusted because some of the AC signal can go through this way and bypass some of this. But it still doesn't really change what happens as far as the op-amp goes. Now, this configuration here, since it has the input on the non-inverting input and it has some negative feedback from the output to the inverting input, that classifies this as a non-inverting amplifier. And all this stuff down here is effectively the second resistor. There's a non-inverting op-amp with gain will have a feedback resistor and a resistor from the inverting input to ground. And so if you strip away all the compensation capacitors and the FET and the circuitry to drive the FET, you essentially just have a resistor from here to ground, and that's comprised of this resistor and this trim pot. So to simplify that, I've redrawn it here. In the ×1 mode, where we're not providing any amplification to the signal, in other words, if it's in the 0 to 2 volt range already, and we just want to pass that through, this FET here is turned off, so it's at infinite resistance, and therefore these resistors just don't count. So all we have is the feedback resistor. And with the high input impedance of this op-amp's inverting input, this resistor is essentially like nothing. So you could just treat this as inconsequential, and therefore it's just like a short circuit. So we basically just have a voltage follower here. Whatever is on the input will be passed through to the output and on to the true RMS converter. So that's the ×1 mode. In the ×10 mode, we bring this extra resistor in here, and that's done by, through this circuit, commanding this FET to turn on, and it goes to a nearly 0 ohms state as if it was a short circuit, and now these resistors here get down to ground. And this calculates out to 962 ohms, assuming that the ×10 trim pot or ×10 cal trim pot is set to 87 ohms. It's a 100 ohm trim pot, so that's certainly not mid-range exactly, but well within its adjustable range. With 8,660 ohms here as what we're just calling R2 for sake of discussion, and 962 here, which we're calling R1, the normal gain formula for a non-inverting amplifier using an op-amp is R2 over R1 plus 1. So that's 8660 over 962 plus 1. If you do the math, that comes out to 10. So we have a gain of 10 when the FET is conducting. For a small amount of AC compensation, there's a capacitor across these resistors, and its capacitive reactance starts coming into play at certain frequencies of AC signal. So it makes a tiny adjustment to the gain, and that's what these are for. But for the sake of this discussion, pretend like they don't exist. Now, if we are passing a DC signal through here, we want to minimize the jitter on the signal, and therefore there's a active filter element that's introduced to this amplifier along with its normal gain, and the logic elsewhere in the meter generates a filter signal that says filtering is required of this buffer amplifier, and it turns on this FET, which connects the output through back-to-back capacitors that just acts like one capacitor, and then a resistor to ground, and then that value or that signal is then fed back to here. So this is frequency sensitive, and it just provides a filtering type function that gets added on to what the amp is doing in its purely DC functionality. In both cases, the FETs are controlled by a diode from the logic that determines if the filter is required or if the times 10 mode is required. Both cases there is a diode facing into that drive circuit that we'll discuss later, and a capacitor to ground, and a 100 meg resistor in this case over a 100k resistor. I'm sorry, a 10 meg resistor. So the drive circuit is slightly different here, but that's just because of where the FET is in the circuit. The logic circuitry that determines the filter command and the times 10 command, the voltage there swings between plus 8 volts and minus 12 volts. When it's at plus 8 volts, that results in the FET's gain or gate to source voltage being 0. So the FET is in saturation and it's conducting from its drain to its source with a very low impedance, essentially a short circuit. So when we have plus 8 volts at the filter command or at the times 10 command, the FET will be conducting, and it brings its part of the circuit into the overall circuit, either to introduce a filter or to introduce the resistor here that causes a gain of times 10. However, if the signal driving goes to minus 12 volts, then the FET will end up being in cutoff, in other words, a very high impedance, so it's essentially not conducting, and its subcircuit is not brought into the bigger picture. Now, the signal coming out of the buffer amplifier, if we're dealing with a DC signal, skips the AC converter and just comes right out here and exits this subcircuit. And going back to our input ranges sketch, that would be this point here. So the signal comes in, it goes through the buffer amplifier, it comes out, it gets a little filtering, and then makes its way through these switches and onto the A to D converter. But if the signal is AC, then it's presented, well, it's always presented to the input of this circuit. And this is a single chip, in other words monolithic, true RMS AC converter. I pointed this out as a round IC package when I was doing the internal views of the meter. It's an Analog Devices model AD536A. It is powered from plus 12 volts and minus 12 volts. It also has a connection to circuit common or ground. The signal coming in from the buffer amplifier goes through a resistor to the input here, and that converts the voltage to a input current, even though it's called VN. It's actually treated like an input current. That's why it's in series. So this is your cal for the AC voltage or AC current. It's the one and only place where the AC is calibrated like that. There's also an offset for zeroing, and that's a 10 or 100K potentiometer between plus 12 volts and minus 12 volts, and then that's divided down by a resistor voltage divider, where the vast majority of voltage is dropped here and only a small percentage of it is developed across this resistor. Therefore this R sub L is a small voltage that can go above or below ground but doesn't get too far away from it. And that causes the internal circuitry here to be zeroable. So that when you have no signal, that you don't end up with something coming out of here. There's a C averaging capacitor, which is tied from this pin to plus 12 volts. That is part of the internal functionality. There's also an output. The chip outputs a current. That's your I sub out. And then that goes through this circuit here into a buffer amplifier, which, amongst other things, converts it to an output voltage. So you have your output voltage coming here. Then that continues on to the AC converter output into the switching. And we'll go back to that previous sketch. And that would be this point here. So if we are using the output of the true RMS AC converter, its signal comes out here. And because of this switching, we use that signal instead of the signal coming from the DC path straight from the buffer amplifier. So that's the overview of the buffer amplifier and AC converter. Okay, the power supply. The meter gets its power either from the internal battery or from an AC power adapter, which puts out somewhere in the 8 to 9 volt range. Because I power mine from a 9 volt regulated wall wart, I'm just writing 9 volts in here. But in practice, the actual official Heathkit wall wart might have put out a little bit closer to 8 volts. There is a rechargeability option here. If this is just an alkaline battery, we don't need rechargeability. When you plug in the AC adapter, this internal switch on the power jack opens up, and therefore the battery's plus side is disconnected, and the voltage from the power adapter just comes through here and comes to the power switch. And if the power switch is turned on, then it continues over here into the rest of the power supply circuit. And there would be something coming back through one of these resistors, some current tapped off of that power adapter, and it gets fed back to the battery to charge it. So remember that when the power adapter is plugged in, this switch is open, so the plus side of the battery is not connected directly to the power adapter. If the power switch is off, in other words the meter's not being used, then we can use all the power coming in from the AC adapter, and that current goes through a 6.8 ohm 1 watt resistor and is fed back to charge the battery. For that to happen, this jumper on the circuit board must be moved from the regular position, regular meaning an alkaline battery, to the NiCad position, meaning the rechargeable battery. Therefore, that charging current goes through here and charges the battery. However, if the power switch is on, then the power from the AC adapter is going this way, and we tap off a smaller amount of current through this 100 ohm resistor and use that to trickle charge the battery. And the battery cannot supply power to the meter if the AC adapter is plugged in. And this diode here prevents that from happening. Okay, the first thing that happens in here, and this circuit is nearly identical to the circuit in the IM-2260 that I already did a video on. It's kind of a sort of a switching power supply, certainly an oscillator with a transformer. The power from the power switch comes in here. There's a 47 microfarad filter capacitor, and then there's this little circuit comprised of two transistors, a small transformer, a Zener diode, and another filter cap. The energy is put into this transformer by turning this transistor on, and that dumps current into the primary of the transformer, which then continues on to circuit ground. So in order for this transformer to work, this transistor must be turning on and off, or at least more on and more off in an oscillatory fashion. And that amounts to an alternating current arrangement here, which results in voltage being developed in the secondary of the transformer. The one side of that secondary is also tied to circuit ground, and we tap off a small amount of that voltage and feed it back to this comparator made out of this transistor. Now this comparator has this voltage that's being developed at the transformer on its emitter, and meanwhile it's using this resistor and this Zener diode, which comes way back here from the negative output voltage of the power supply. It's using that as feedback and applied to this 12.8 volt Zener. You develop a voltage here on the base of the transistor, which is compared by the transistor to the voltage on its emitter. And if the voltage here is 0.6 volts higher or more than that from the voltage being developed at this point on the transformer, then this transistor conducts, and when it conducts, it causes this transistor to turn on, which dumps power into the transformer. The way this is set up, it results in an oscillation, and it also fine-tunes the oscillation because of this feedback. So the point at which this transistor conducts, causing this one to conduct, is directly influenced by the feedback voltage, and that's how it can essentially regulate the output voltage using only the minus 12 volt output of the supply as its reference point. It assumes that if the minus 12 volts is correct, then the other voltages will be approximately correct. The plus 12 volts, the plus 8 volts, and the minus 8 volts. And nothing in this meter requires those to be super tightly accurate in their regulation. It just needs to be pretty close. So that's what's going on here. It's both an oscillator and a voltage regulator circuit. Coming off of the full secondary winding is a half-wave rectifier with a filter cap to ground, and that provides plus 12 volts to the rest of the meter circuit. And again, that should be kept pretty close to 12 volts because the complementary circuit for developing the minus side is tied back to the voltage regulating circuit. There is, again, this complementary side for the minus 12 volts. Instead of tapping off the secondary of the transformer, it's tapping off the primary right where the transistor dumps into it. And that has a half-wave rectifier going the other direction, hence the negative voltage. And that gets you your minus 12 volts. And there's again a filter capacitor to ground. Now we also need plus and minus 8 volts. So there's this simple little circuit here. This is just a series pass transistor using the plus 12 volts as its source. Goes through a 100 ohm resistor, through the series pass transistor, and out to 8 volts. Well, for that to work, we have to hold the base of the transistor at whatever we want here, plus the forward voltage drop from the base to the emitter. So roughly 0.6 volts. There's an 8.2 volt Zener diode here, and then there's a regular silicon diode that will be forward biased, so about 0.6 volts across it. You add the 8.2 and the 0.6 and you get 8.8 volts developed at the base. So in reality, you're going to drop 0.6 volts, the base to emitter forward voltage, from the 8.8, and you really get about 8.2 volts, but we're calling that 8 volts, and so does Heathkit. This little bit here with the resistor and the capacitor, and this diode back here just refines the operation of this circuit, but the part I already described is the essence of it. And then we have a complementary version of that using a PNP transistor and all the diodes pointing the other direction to generate the minus 8 volts off of the minus 12 volt supply. As already mentioned, the 7106 analog to digital converter requires a reference voltage applied to its reference input. And I already mentioned that because in this meter, the regular input is expected to swing in the 0 to 2 volt range. It's actually minus 2 volts to plus 2 volts, but counting from 0, it's a 2 volt span. Since that's the case, it needs to have the reference input voltage be 1 volt. So we need to develop that somehow. There's this little circuit here. It takes off the 8 volt power supply we've already developed, passes it through this resistor, and then this IC voltage reference, which looks like a Zener diode in the schematic, but it's actually a temperature compensated integrated circuit voltage reference, and it develops 1.2 volts across it. That is filtered by this capacitor and then applied to this resistor divider. At the top of the resistor divider is the 1.2 volts reference to ground, and that's the high voltage cal test point that's used during calibration of the meter. And then because of this pair of resistors in this divider, we end up with a low calibration voltage of 0.19 volts. Heathkit calls it 0.18 something, but it's calculating out to 0.19. Close enough. So those are the internal voltage references used for calibration. And now with this voltage divider, also using the 1.2 volts, 1600 ohms, and an equivalent 744 ohms made out of the 100K trim pot and a 750 ohm resistor in parallel with it that is effectively 744 ohms. And then 8660 ohms here. If you do the math, that works out to 1.025 volts here and 0.944 volts here. And that's presented across this trim pot. And if you do the math, figuring out what's halfway between those two voltages, it's 1 volt. So that's where the 1 volt into the reference input of the analog to digital converter comes from. And you get that 1 volt when this trim pot is in its center of rotation. So there's a little bit more to this here. I chose to put this sub-circuit on the power supply because it's related to low battery detection. So in order to get the low battery indication on the display, we have this transistor comparator circuit. There's a voltage divider here with 113K on the top and bottom tied to the 12 volt power supply. So you end up with half of the voltage, or 6 volts, on the base of the transistor. With the base of the transistor held at 6 volts, the battery voltage coming right off the power switch is applied to the collector of this PNP transistor. As long as this voltage is more than the base voltage plus the base to emitter voltage drop of 0.6 volts, in other words, if the battery voltage is greater than 6.6 volts, then this junction is forward biased, and that causes the transistor to conduct. So the collector resistor here has across it the full battery voltage. In other words, the battery voltage when this transistor is conducting is developed across this 100K resistor. That voltage forward biases this transistor, which pulls its collector to ground instead of the plus 8 volts it's normally pulled up to. Therefore, this diode is not forward biased, and it cannot pull the input to this logic gate high, and instead the 1 meg pulled down resistor, which is going to the V test voltage output of the 7106, and as already mentioned, that's a positive 3 volt signal. That acts as a logic low to this IC, since it is being powered off of plus 8 volts and the V-test, or plus 3 volt potential, which is a 5 volt power supply as far as it's concerned. But it treats plus 3 volts as a logic low. Therefore, it does not generate the low battery signal. However, if the battery voltage drops below 6.6 volts, then this transistor is no longer having its base to emitter junction forward biased. It stops conducting, and this resistor here then pulls the base of this transistor low, turning it off. Therefore it is not conducting. Therefore this resistor can pull the anode of this diode up to plus 8 volts. Therefore it is forward biased, and it conducts and pulls this junction up against this 1 meg resistor that's trying to pull it down. It pulls it up to approximately 0.8 volts, which again is the logic high signal as far as this integrated circuit's concerned. So we've gone from it being logic low when you have enough battery voltage to being a logic high when we don't have enough battery voltage. And that combined in this XOR gate with the backplane signal coming off the 7106 generates the LCD low battery segment drive signal, which is the same voltage swing as the backplane, but 180 degrees out of phase with it. Therefore, the low battery segment will become visible. Okay, here's another sheet of logic sketch. This has to do with the so-called auto range functionality, which on this meter is whether or not it's in the ×1 or the ×10 mode of the buffer amplifier. And it also has to do with which decimal point is turned on at the moment. And also whether or not the filter on the buffer amplifier is turned on or off. And finally, also on this sketch, is whether the LCD will display a minus sign for a negative voltage and have that be the only thing, or whether it will display a plus sign for positive voltages. So that's also on this sketch. So to recap what I said just a moment ago, the way the LCDs work, a segment of the LCD will become visible if you have a voltage developed across the segment and the backplane of the LCD. But it can damage the LCD if you constantly maintain the same polarity of voltage on it. So normal practice is to apply a voltage but have it constantly reverse polarity at some frequency. On LCDs driven from the 7106, the backplane signal alternates between whatever voltage is the positive voltage applied to the 7106. In this circuit, that's plus 8 volts. And the V-test signal, which is 5 volts less than the positive voltage, in this case 3 volts. So the square wave backplane signals alternating between plus 3 volts and plus 8 volts. And if you want a segment to appear visible, you drive it with the same kind of signal but 180 degrees out of phase with the backplane signal. In other words, when the backplane is high, the signal driving the segment will be low, and vice versa. So with all of that in mind, we have these three signals driving the 3 decimal points on the LCD. And here's a little sketch of the 3.5 digits on the LCD. The units, tens, hundreds, and thousands position. The thousands can only be a number 1 or nothing. The other ones can be anything between 0 and 9. And we have these 3 decimal points between them. There's no point in showing a decimal point at the far right, so decimal point 1 is not used. And there may be a decimal point 5, but it's also not used. No point in having it there in this particular meter. So decimal points 2, 3, and 4, and those are driven by these 3 signals. Just like the drive signals for the low battery indicator I've already discussed, those come from this XOR gate. It's a quad XOR logic chip. One of those quad gates has already been discussed for the low battery indicator. The other 3 of them are here. And one side of their, or one of their inputs is tied to the backplane, just like with the low battery. The other side, or the other input of each one, is tied low through a 100K resistor to the V-test, which is logic low as far as this IC is concerned. So normally it's seeing a logic 0 on these inputs, and therefore none of the decimal points are turned on. They're actually getting a signal all the time, but it will be in phase with the backplane, so those decimal points will not be visible. Turning on this input, for example, making it a logic high, would cause the output signal to be out of phase with the backplane. Therefore, that particular decimal point would become visible. Same thing applies to the other 2. So here we have the range switches. The 200 millivolt, 200 microamp, 200 ohm, the 222, the 20s, the 200s, and what is essentially always 2000, but in the case of voltage it's limited below that. And then finally the battery test, or the 10 amp or the 20 mega ohm switch. So all these switches are here. This circuit doesn't actually require the 2000 position, so it is just not connected. The other signals here all come down and have pulled down resistors to minus 8 volts. So if the switch here is open, the voltage coming off the switch is minus 8 volts. But if a switch is closed, then it pulls that switch output up to plus 8 volts. So these signals here are swinging between minus 8 and plus 8 volts, depending on which of these switches is closed. There's a bit of diode logic here. So the decimal point 4 is turned on whenever we're in the 2 volt or 2 milliamp or 2K range. And that makes sense because we're only going to be reading a full scale of 2, and that's really at 1.999, so that's where we want the decimal point to be. If we're in the 20 range, where we're expecting to see a full scale of 20 volts or milliamps or K, then this switch will be closed, and that goes through this diode and turns the input to the decimal point 3 to turn on, and that's what you'd expect to have if you're trying to read a value of 20, which is really 19.99. So 19.99 is where you want the decimal point to be, right here, decimal point 3. And also, if we're in the battery test mode or the 10 amp range or the 20 mega ohm range, it's still looking for a full scale of 20. Either 20 volts for reading the battery voltage, which would be closer to 6 volts or something, or 9 volts, but still within a 20 volt range. And even though we only go up to 10 amps, it's still on a 20 amp possible range, and in the case of 20 megs, we are going up to 20. So once again, we want decimal point 3 to be on when you're in that range, hence this other diode that turns the same decimal point on. And then for decimal point 2, we have a similar arrangement. If we're in the 200 millivolt, microamp, or ohms range, we're coupled down here. And since we're expecting to read 200, that would be 199. So we want decimal point 2 to be on. I'm sorry, it would be 199 here, point something. So we want decimal point 2 to be on. And that's what's accomplished here. Or if we're in this other 200 range, 200 volts, 200 milliamps, 200K, we go through the other diode and cause the same thing to occur. So that's how the decimal points are controlled. Now we have a sort of similar arrangement here for the functions. You've got the DC volt switch, AC volt switch, DC amp switch, AC amp switch, and ohm switch, also tied to plus 8 volts and with pull down resistors to minus 8 volts. So it's the same kind of circuit as over here. But now we're concerned with which function we should be in, as far as are we turning on the times 10 mode in the buffer amplifier? Are we turning on the filter on the buffer amplifier? So I'm not going to bore you with working out all the logic here, and especially this fun little bit here, which is using a lot of negative logic and so on. I've worked it through and it definitely works. It's comparing if we're in DC volts or AC volts, then this input to the gate turns on. It's comparing that with whether we're in the 200, low 200 range, or the the 20 range, or the battery 10 amp 200 or 20 mega ohm range. It works out where that gets compared with whether you're in AC or DC volts or not, and then that's also compared with if you're in ohms, or again the battery test 10 amp 200 mega ohm function. All of that gets wrapped into here, and there's some truth table logic that's done here. And if it's determined that the buffer amp needs to be in the times 10 mode for whichever combination of functions and ranges works its way through this logic, then this transistor would be turned on or not, and it'll pull the times 10 drive signal between plus 8 volts and minus 12 volts as already discussed. To turn on the function, it'll be at plus 8 volts. To turn off the function, it'll be at minus 12 volts. And just to simplify what this logic ultimately does, the functions and ranges that use the analog to digital's times 10 mode are the 200 millivolt and the 20 volt range. All amps ranges and all ohms ranges except for the 20 meg range require the buffer amp to be in times 10. And that truth table that would be driven by this statement is what this logic accomplishes. Similarly, this little bit of logic down here, it's just diode logic in this case, no gates required. If we're in, for example, DC volts or DC amps, then we go through these two paths and then down this way, and we work our way through these two transistors and end up producing a plus 8 volts signal on the filter control line to turn the filter function on the buffer amplifier. Otherwise, it's minus 12 volts and the filter functionality is turned off. We also engage the filter if we're in the ohms mode. It just goes straight through here and does the same thing. The filter is engaged for DC volts, DC amps, or ohms. In other words, any time when the signal is not alternating. We also have the plus command, which is saying we want to have the plus sign appear on the display if it's not displaying a minus sign. And that will be turned on for DC volts or DC amps. But if we're in ohms, we don't want to have that happen, for example. So ohms is excluded. You might turn on ohms, but it can't make its way back through these diodes to turn this function on. So here's the logic that works with the plus sign and the minus sign on the display. This signal here is coming out of the 7106. It is its sign or negative sign segment driver. As such, it has always got a square wave output on it going between plus 3 volts and plus 8 volts, and either in phase or out of phase with the backplane, depending on whether the sign should be displayed or not, according to the 7106. That's what it wants to have happen. We also have the backplane signal here from the 7106, so we know that. This first XOR gate compares whether the sign is in phase or out of phase with the backplane, and if it is out of phase, then its output turns on, meaning that we know from this point if it's a logic high, then the 7106 is trying to indicate a minus, and otherwise it's trying to not indicate a minus. In other words, it's a plus or a positive. That is combined with these other two gates and the plus command that was developed over here, and then these two resistors here, which are playing games with the input logic thresholds of these gates here. And I won't bore you with all the details, except that what that's doing is it's saying When we're in a function where displaying a plus sign is appropriate, and when the 7106 is not trying to display a minus sign, then we will have a logic 1 here, up here, and it will turn on all the segments necessary to display a plus sign. But if we're commanding it to have a plus capability, a plus sign capability, and we are displaying, and the 7106 is trying to show a minus sign, then we will only turn on the minus sign on the LCD. When we're trying to display a plus sign, actually both of these signals need to be on. And the reason for that is that the LCD actually has 3 segments for the sign. There's the dash, which is only used, which is used by itself to display a minus sign, and then there's 2 more vertical segments, and those 2 get turned on together along with the minus sign to form a plus sign. So again, this logic detects whether a minus sign is currently desirable from the 7106. It checks to see if we're in a mode where we want to display a plus sign if a minus sign is not being commanded, and then from that it generates the necessary segment drive signals to operate the plus segments and the minus segments. Now, not strictly part of the functionality of the meter, but part of the calibration. I've already shown the resistors that are used for calibration in the ohms mode, and the high and low cal test points that are used for calibrating the voltage mode. And in the amps mode there is no reference. It's just assumed that if the voltage mode is calibrated and if the current shunts for the amps mode are accurate and they are precision parts, then the amps values will be appropriate without requiring any calibration. But the true RMS AC converter IC does need to be calibrated. It has that trim pot on its input, and so the meter includes an AC signal generator which is used for the calibration of that signal, or that mode rather. So what we have here is basically a classic 2-inverter oscillator. This type of oscillator is what's known as a 2-inverter RC oscillator, and I've made an equivalent circuit of it here. This is right out of the textbooks. These 2 NAND gates are wired as inverters, so we can view them as simple inverters here. And this 100K resistor is this one, and this capacitor here is this capacitor. We may use one or both of these, but in this diagram it's represented as one capacitor. And then there should be a resistor from in between these 2 going to this point, and it should be the same value as this. Well, we also have 100K resistors here. On one half of the oscillation, when this point is at a positive voltage, this diode will be forward biased, and therefore this 100K resistor will be filling in for this guy. On the negative swing of the oscillation, this diode will bring this resistor in. And you say, well, why are we doing that? Well, because they're also added to this symmetry pot of 50 kiloohms. So if this pot is centered, you really have 25K on each side of the wiper, so it's really 125K resistor here and 125K resistor here. Whichever half the waveform are on, it looks like a 125K resistor here. And then if you push the symmetry adjust pot one way or the other, one of these gets a little bigger, the other gets a little smaller. Therefore, this resistance varies between the positive half of the AC cycle and the negative half of the AC cycle, and that changes the symmetry of the oscillation, so the square wave that comes out of the oscillator isn't a 50% duty cycle. It may be on a little bit longer than it's off, or vice versa. For the moment, let's just treat it like this pot and these diodes are not there, and we just have a simple resistor, and that it's about 100 k ohms. There's this jumper here for low frequency, high frequency, and off. If the jumper's in the off position, this point here is tied to -8 volts, which is the logic low for this circuit, since this gate IC is powered from plus and -8 volts. So -8 volts is actually what this circuit thinks of as ground, or at least the logic gates do. If you tie this point to logic low, or -8 volts in this case, then this stops oscillating. However, if you have it tied to the high F position, then it's open. This point doesn't go anywhere in the circuit, so it's exactly like you see it here. If you put the jumper in the low F position, then what we've really done is we've just shorted out this 1000 picofarad capacitor, and everything else remains as it is. So you either have a 1000 picofarad capacitor in series with a 0.047 microfarad capacitor, or you have only the 0.047 microfarad capacitor, depending on whether you want a higher or a lower frequency of oscillation. So going back down here, I've already written once again, if we're in the low F position, it's 0.047 microfarads. If we're in the high F position, this is 980 picofarads. How do I get that? Well, you know, if you put two resistors in parallel, the effective resistance is less than the smaller value, and how much less is defined by the larger value. The same thing happens with capacitors when they're connected in series. So it works out here that the series combination of these two capacitors, which is only important when you're using both of them, in other words, when the 1000 picofarad is not shorted out, that works out to be 980 picofarads in the high frequency mode. This is the formula for calculating the frequency of oscillation of a circuit like this. It's the reciprocal of 2.2 times the capacitance C times the resistance R, and it's assuming both of these have the same resistance value or close to it. If I plug in the values 0.047 microfarads into the formula for low F, I come out with 97 hertz. If I plug in the 980 picofarads for the high frequency mode, I get 4.6 kilohertz. So those are the approximate values of the frequency of oscillation for this, depending on how the jumper is set up. So I made a little diagram here. I said the output of this oscillator at this point, the so-called symmetry test point, is a square wave going between -8 volts at the bottom and +8 volts at the top, and it's either 97 hertz or it's 4.6 kilohertz. Now we have this voltage divider here, 100K with a 50K adjust. You do the math and it works out where going peak to peak, remember this is plus and minus 8 volts, or it's a 16 volt peak to peak square wave. If this pot is set full up, you get 16 volts peak to peak. If it's set to the other side, you get about 10 volts peak to peak, so you can vary it that much. These two capacitors back to back, they're electrolytics, they're 10 microfarad. Because it's an AC signal that's going above and below ground, the polarity on the capacitors will change. And normally you don't want to expose an electrolytic capacitor to reverse voltage for any length of time. And the usual trick that's done is when you do need to have an electrolytic voltage in an AC circuit, that you use two of them and put them back to back in a series arrangement like this, and then they're not damaged by the alternating polarity. And because they're capacitors in series, they work out to be an effective 5 microfarad capacitor here. So that's put in here, and there's a resistor to ground, and we're measuring off the junction between the capacitor and the resistor. That's our reference test point. At the frequencies we're talking about here, these capacitors do practically nothing. So the output is still a square wave. The corners are ever so slightly rounded, but it's still really a square wave. And so that's what's used for calibration of the true RMS AC converter IC. So it's a square wave at one of the two aforementioned frequencies. The DC component, if there has been any DC component, it's removed by these two capacitors. So we get a true symmetrical above and below ground voltage applied across this resistor, and therefore measurable out here. Now, there's also this little circuit tacked on to the same signal, and this is a peak detector. So it only conducts on the positive half wave, and it takes whatever voltage is out here on the positive half wave and puts that voltage into this capacitor, which stores it. It can't discharge back this way on the negative half cycle, so it just stores whatever peak voltage is there, and then that's a DC reference voltage that's related to the amplitude of the frequency test point voltage. There's a reference symmetry test point that's developed by the plus and minus power supply rails with equal value resistors. So you should get 0 volts here. But if it works out where the power supply regulation is not that great, and maybe the 0.8 is really 8.5 volts, and the -7 or -8 volts is really -7 volts, then this will not be 0 volts. The actual waveform coming out of this oscillator is assumed to be plus and minus 8 volts if the power supplies are really putting out the voltage they're supposed to have. But we know that's not going to be precise, and we compensate for that by adjusting the symmetry, so the average voltage will be centered at 0 volts. Remember that the output voltage of the oscillator is based on the voltage, the power supply voltage applied to the oscillator ICs, which again are coming off the plus and minus 8 volt supply. So the square wave can actually be a little bit higher or lower than plus 8 volts, and same thing goes with the minus 8 volts. So during calibration, you use the DC function of the meter itself to measure this point and see where the halfway point is between the plus 8 volt and minus 8 volt supplies. It may not be exactly 0. So after taking the reading here and seeing what the midpoint voltage is, we connect the voltmeter again in DC mode, so it's just looking at the average, and we go to the symmetry test point and we're reading the square wave, and the internal capacitance of the meter in DC mode will just reflect the average of the voltage between the plus and minus, and not just the voltage, but how long it's plus and how long it's minus. So that's what this symmetry control here is for. We now adjust the symmetry control until the duty cycle, how long it's positive and how long it's negative in the oscillation. With that combined with what the actual plus and minus voltages are, you'll end up with the DC reading part of the meter getting a voltage that's should be, as an average, the same as what we got down here off of this point. So you adjust this pot to compensate for any disparity between the plus and minus 8 volt supply rails. So that's what is accomplished with this and this. Then you go over and you put the, well, I won't go into all the details, but then you start comparing the voltage here, the DC voltage here, with the AC voltage measured here. And you go back and forth. It's an iterative cycle, and they're adjusted against each other. And you do that at the 97 hertz, relatively low frequency, not too far from 50 hertz or 60 hertz like you'd get most commonly in measuring AC signals that are related to the power line frequency. And then you change the jumper here and bump it up to 4.6 kilohertz, and you do the same series of measurements and adjustments again. You readjust for symmetry, and then, well, I should have said before that, well, no, I'll skip that, it's too complicated. Remember I said that in the input range circuits for voltages, this resistor divider here actually has some capacitors across these resistors. Some fixed capacitors and some trimmable capacitors. These are the same resistors on the actual schematic, and there is a trim capacitor for high frequency AC and a trim capacitor for low frequency AC. And those are adjusted during the calibration to tweak the voltage divider here to get exactly the right frequency when you're measuring AC volts, or AC current really, but primarily AC volts. So those are just fine tweaks to get all that adjusted for optimum precision. So that's what that circuit does, and basically how it's used. And I can't really think of anything else to say about the circuit. I've covered all the major points.